Welcome to your 3.2 Graphing Logarithmic Functions video notes. I hope everyone's having a great day today. Okay, so we are going to start by graphing logarithmic functions. So we have already talked about what a logarithm is. Remember, a logarithmic function is the inverse of an exponential function. So remember, inverses is just essentially swapping the x and y values of the original. So to graph a logarithmic function, you can use an exponential function, then swap the x and y values from the exponential table to graph the logarithmic function. So, let's finish this one. So the x values from an exponential function will now be the y values of the logarithmic. So we've already talked about how to graph the parent function of an exponential function. Remember, the x values are -1, 0, 1, and then we have 1 over a, 1, and a. Assuming, of course, that the parent function here is f of x is equal to a to the x power, where again, a can be any base. So it can be any number, positive, always positive, because remember the negative causes like a reflection, but it can be a whole number, it can be a fraction, whatever. Okay, so and then of course we know the domain of any exponential is going to be all real numbers. The range of any exponential is going to be 0 to infinity. And we have a horizontal asymptote at y equals 0. So in an exponential, we know it's a horizontal asymptote. So this is stuff that you've already covered. You've already seen the parent function of an exponential function. So now what we can apply is if we know that a logarithmic function is the inverse of an exponential function, to figure out the table, all that we're going to do here is we are going to swap the x and y values. So the parent function of a logarithm is, if you look over here, the parent function is here, where again, the base is a, so it's log base a of x. And just like with an exponential, a represents any positive value. So a represents any positive value. Okay, so when we go ahead over here, my x values are going to be my y values of my exponential. So my x values are going to be 1 over a, whatever a is. Let's actually write this parent function over here too. Is f of x equals log base a of x. So a now is looking at the base of the logarithm. And then 1 and a. So the y values are now the x values. And my x values are now the y values, -1, 0, and 1. Now, to find the domain and range, just like we did before, the inverse, the range of the inverse is the same as the domain. So that means for a logarithmic, the range is going to be all real numbers. Remember, the inverse, you're just swapping the x and y values. If domain is looking at my x values, when we swapped it, now those are my y values. And then just the opposite. The range of my exponential is going to be equal to the domain of my logarithm. So it's going to be 0 to infinity. Now, this one also has an asymptote. But if you think about this, this one had a horizontal asymptote, but we switched the x and the y's. So if this is y equals 0, this asymptote is going to be x equals 0, which means this is going to be a vertical asymptote. Okay, so again, just like I said with the exponential, I will give you the parent function table for the logarithmic function. So you'll have both parent function tables. Okay, so let's get into graphing. It says use transformations to graph the following logarithmic functions, then state the domain, range, any asymptotes, and describe each transformation. Okay, so the first thing we need to recognize is what is the base in the logarithm. So the base here is 4. So I usually will say either like what the parent function is, but sometimes it just helps to think, okay, in this case, A is 4. So I'm going to use that and apply it to this table up here. Okay, so that's going to be my starting point. My x values are going to be 1 over 4, because A in this case is 4, 1, and then 4. And my y values are going to be -1, 0, and 1. So typically, most of the time, our x values are the ones that are like unchanged. They're always the same. But in this case, since we're swapping, the y values are really going to be the ones that remain unchanged. They're always going to be -1, 0, 1 for our parent function. Okay, so now we apply our transformations just like we have been doing in every other parent function. So we think to ourselves, okay, is the -1 going to be a change to x or a change to y? So remember, when it's a change to x, it's within the function. When it's a change to y, it's outside the function. So this -1 is within the argument. It's within the parentheses. So when it's within the argument or within the parentheses here, this is going to be a change to x. And then that -2 is outside the parentheses. And so that -2 is going to be a change to y. Okay, so let's apply that to our parent function table. So remember, to all of my x values, we do the opposite operation. So if this is -1 to my x values, I'm going to add 1. And then to all of my y values, we do the same operation. So to all of my y values, I'm going to subtract 2. Now you can do the table in the middle, or if you just want to do it in one, mathematical problem, you can do that. So what we're doing is we're taking this 1/4. Now I'm going to write it as a decimal. If you need to figure out what it is as a decimal, use your calculator. 1 divided by 4, or you should know that that's 0.25. So to 0.25, 1 and 4, we're going to add 1 to all of those values. And then to our y values, -1, 0, and 1, we're going to subtract 2 from all of those y values. And then we can get our final table. So that would be 1.25, 2, and 5. And then my y values would be -3, -2, and -1. Okay, now just like with exponential, I said always graph the asymptote first. So it's the same idea here with a logarithm. So my asymptote I have is x equals 0. So I think, okay, what did I do to all of my x values? I took them and I added them by 1. So my new asymptote is going to be x equals 1. So remember, it's a vertical asymptote, so that means it's going up and down. And it's going to be right there. Now, another way to find the asymptote, you can do that by not even figuring anything out. So if you want to find the asymptote without graphing or without doing your transformations, what you can do, I'll just do this here. Asymptote, okay. You can take your argument, x minus 1, set it equal to 0, and then solve. And you get x equals 1. Same thing. However you want to do it, you can do it either way. So all that we're doing there to find that without doing any transformations, you set the argument equal to 0 and solve for x. Okay, so let's plot our points. So we have 1.25 is at -3. We have 2 is at -2. and then we have 5 is at negative 1. Now your exponential, remember, was like a graph like this. It was like kind of hugging the horizontal asymptote and then went at a like sharp curve up. So that is just, it's really similar for a logarithmic. It's just kind of to the side. So instead it's hugging that vertical asymptote and then it's a sharp turn to the side like that. Okay, so the domain, well actually let's look at the range. The range is always easy. The range is always going to be all real numbers. No thinking, as long as you remember like which range, like the range for or logarithmic is easy. The domain for exponential is easy. It's always all real numbers. Okay, so just like with an exponential, the horizontal asymptote went with the range. With this one, the vertical asymptote goes with the domain. So the domain here is 1 with a parentheses to infinity. Now you can also figure out what the, okay, I had a visitor, so I honestly have no idea where I just finished my like last sentence. And I'm sure this is so weird because I just like, I paused it and I'm starting back up again. So who knows where I was at, but I think I was talking about the domain. So the domain, like I said, it goes hand in hand with the vertical asymptote. So if this is 1, you will always either like start or end with 1 or whatever the vertical asymptote is. But you can also, without graphing, figure out what the domain is. So just like the asymptote, you set the argument equal to 0 and then solve for x. This, what you're going to do is take the argument and you're going to just basically set it greater than or equal to 0. So you're going to take the argument, which is x minus 1 is greater than 0, and then solve for x. X is greater than 1. So to find the domain, you're just going to set the argument greater than 0, because the argument always has to be positive, and it can't be 0, so it has to be greater than 0. Set argument greater than 0 and solve for x. Okay, so now that you've found your domain, your range, your vertical asymptote, we've graphed, we can talk about the transformations. So the transformations are no different than what you've been doing already in the past. So the negative 1, remember when it's a change to the x, it's moving it left or right. So the negative 1 is moving the graph right 1 unit. And then the minus 2, because it's a change to y, it's moving it up or down. The minus 2 moved the graph down 2 units. Okay, so that is our first graphing of logarithms. So again, a lot of it is just knowing your parent function, and I will give you the table so you don't have to have that memorized. You just have to know how to apply it and apply your transformations. Okay, so let's move on to problem number 2. So problem number 2, what I'm going to have you guys do is start by just figuring out what is the a value and what's your parent function table. So pause me here, figure out what your a value is, and then what from there is your parent function table, and then come back and check your work. Okay, so you should have paused and figured out what your parent function table is. Our a value here is our base, which is 3. So from there, my parent function table. Now, often when I'm doing this, I'll write the y values first, because I know that those are like my consistent ones. And then I write my x values. So it's going to be 1 over 3, 1, and 3. Okay, so now we need to apply our transformations. So in this case, I have 3 transformations. I have the 1/2, I have the negative, and I have the +1. So now what I would like you guys to do is, again, pause me here, try and apply your transformations, get your final parent function table or your transformed table, and then come back and check your work. Okay, so hopefully you were coming back to check your work. So first thing you have is that 1/2. So that 1/2 is on the outside of the parentheses. So this 1/2 is going to be a change to y. Now this negative is always a reflection, but because it's within the parentheses, that's going to be a change to x. And then that +1, just like it was on the last one, I want to make sure my colors are consistent. The +1 is on the outside. It's going to be a change to the y values. Okay, so let's apply that to our parent function table. So the only thing that's changing the x is that negative. So remember, you do the opposite operation. So if that's multiplying by -1, we are going to divide all of our values by -1. So the opposite operation of multiplication is division. And then to my y values, I'm going to multiply them by 1/2 because this is saying 1/2 times. So we're going to multiply our y values by 1/2, and then I'm going to add 1. Okay, so all of my x values, so I'm just going to write 1/3 as a decimal, which is repeating, but we're just going to write it as 0.33, and then 1 and 3. So all of those values we're going to divide by -1, which is really the same as multiplying by -1, but works. And then all of my y values, I'm going to first multiply by 1/2. And then I'm going to add by 1. Okay, so now I can do the math and get my final table that I'm going to graph. So this is going to be -0.33, -1, and -3. And then with this, when I do the math here, so if you want, you can do it just in your calculator. You can go, okay, 1/2 times -1 plus 1. That gets me 0.5. And then 1/2 times 0 is 0. 0 plus 1 is 1. 1/2 times 1 is 1/2. And then 1/2 times 1 or plus 1 is 1.5. Now, before I graph, I'm of course going to get my asymptote. My asymptote originally is at x equals 0. The only thing that changed the x's is we divided by -1. And that's not going to change it. So my asymptote is still going to be x equals 0. That was supposed to be this one. I know that really looks so different, but whatever. Okay. Again, you could just take the argument, -x, set it equal to 0, divide both sides by -1, I get x equals 0. However you want to do it, you do you. So I'm going to graph my asymptote. I'll just draw it here. So it's on the axes. And then I'm going to plot my points. So -0.33, now it's on this side, is at 0.5. -1 is at 1. And -3 is at 1.5. So again, it's that curve where it is hugging the asymptote and then it takes that sharp turn. Okay, so now what I want you guys to do, pause me here. I want you guys to think about what's the domain, what's the range, and then what did each thing do to the parent function. So what did the 1/2 do? What did the negative do? And then what did the +1 do? And then come back and check your work. Okay, so the range should always be your easy one. Your range is always all real numbers. And even just by looking at the graph, there's no stopping or starting point from bottom to top. It goes arrow to arrow. So we can also assume it's -infinity to infinity. My domain here, now my domain from left to right is -infinity to 0. Just like I said, it should match up with your asymptote. If my asymptote is at 0, I should have 0 in here. You could have also done -x is greater than 0. Now, I would divide both sides by -1, and when I divide an inequality by a negative value, it's going to flip the inequality symbol, which matches with what I did here. Now, the 1/2 causes a compression of the graph. The negative caused a reflection. Remember, I want you to be specific with what it was reflected over. So if it's a change to x, it caused a reflection over the y-axis. So caused reflection over the y-axis. And then the +1 was a change to the y values. That moves it up or down. So the +1 moved the graph up 1 unit. And that does it for 2. And remember, if you guys have any questions on any of these problems, we can, of course, go over them in class so we can make sure that we fully understand this. Okay, so let's look at 3. So 3 is one of our natural logs. So we think, okay, well, what's the base here? Well, we know it. ln is always going to be the same as log base e. So if you need to write that e, or if you need to write it as log base e of x plus 5 minus 3, then go ahead and do that. But ultimately, all that matters to us is what is my base? What is my a value? And in this case, a is equal to e, or as we know, 2.72 approximately. So that's not going to really change anything from what I've been doing in all of the other problems above. So what I'm going to do, start with my parent function table. My y values are -1, 0, and 1. And then my x values are going to be 1 over e, 1, and e. And so now I can just apply my transformations as I normally do. So the +5, that's within the parentheses, and that's going to be a change to my x values. The -3 is outside. Did I say the x was within? The +5 is within the parentheses, so it's a change to x. The -3 is outside the parentheses, so it's a change to y. And so I'm just going to apply those transformations to my parent function. So to all of my x values, we're going to do the opposite operation. We're going to subtract 5. Remember, if you need to remember where e is on your calculator, so on my calculator, it's second divide. So 1 divided by second, second e, that would be 0.37. If you wanted to do it on the scientific calculator and you wanted to do 1 over e, you totally can. So you just have to do, when you do this, let me get it so there's not a glare. It would be 1 divided by, and remember that in this case you do second ln. So it'd be second ln, but because you have to put an exponent, you would just do to the first power. And it gets you the same thing, that 0.37. And then 1, and then we know e is 2.72. So to all of those, I'm going to subtract 5. And then to all of my y values, so to -1, 0, and 1, for y we do the same operation. I'm going to subtract 3. And then I'm going to get my final table. So if you need to do that in your calculator, which honestly sometimes I do, like 0.37 minus 5 is going to be -4.63. 1 minus 5, that one I can do. And then if you want to do e minus 5, so second divide, minus 5, -2.28. And then -1 minus 3 is -4, -3, and -2. Of course, before I graph my points, I'm going to graph my vertical asymptote. So to figure that out, I think about what happened to all of my x values. My x values, we subtracted them by 5. So 0 minus 5 gets me my new vertical asymptote at x equals -5, which is right there. And then I can plot my points. So I have -4.63 is at -4. -4 is at -3. And then -2.28 is at -2. So again, it's that curve with a sharp turn up or to the side, however you want to think about it. My range, always the same, all real numbers. And then looking at the graph from left to right, it starts at -5 and goes on forever. So it's parentheses -5 to infinity. My vertical asymptote and my domain always go hand in hand. So the -5 and the -5. And then we discuss our transformations. So the +5 moved it left 5 units. And then the -3 was a change to the y. It moved it down 3 units. Oops. Okay. So there you have it. That is that one. And then we're almost done. So 4, very similar. There are 4 different transformations. So what I want you guys to do, I want you guys to pause me here. I want you guys to try it on your own. I'm not going to walk you through every step of this one. I'm going to kind of just like show you the work like I normally would in class. And so I want you though to really try and pause this video here, try all of 4 on your own, and then come back and check your work. Okay, so we have our parent function. Anytime you have ln, you have your base is e. You can always assume when it's ln, your base is e. So I have my parent function just like I had my parent function on 3. Now I'm going to apply my 4 different transformations to that parent function table. So as you can see, I started off my table with applying my transformations. So the negative is one transformation, that's a change to y. The 2 is another transformation, that's still a change to y. The -1, because it's in the parentheses, it's going to be a change to x. And then the +4 is outside the parentheses, that's going to be the third change to the y. Now I'm just going to apply that to my x values or my x and y, and then I'm going to get my final table. Okay, so here's my final parent function table. Before I do anything, of course, I'm going to get my asymptote. My asymptote of my parent function was originally at 0. To all of my x values, I just added 1. So my new asymptote is going to be at x equals 1, which is over here. And then my graph, I have 1.37 is at 6. 2 is at 4, and then 3.72 is at 2. And so it is this curve kind of going down. And now I can fill in for my domain and range. My range, always the same, all real numbers, -infinity to +infinity. And then my domain from left to right starts at 1. It goes hand in hand with the asymptote, and it's 1 to infinity. Last thing is describing the transformations. If you haven't done this on your own, pause, try and think of those on your own. I'm going to not write them all out, but I'm going to pause and then start again so you guys can just see those. Okay, so the negative, always the negative causes a reflection. Because it was a change to the y values, it caused a reflection over the x-axis. The 2, anytime you're multiplying it by a number bigger than 1, is going to cause a stretch. The -1, when it's a change to x, it's moving it left and right. Because it's a minus, it moves it in the opposite direction that you would think, so it moves it right. And then the 4 is a change to y, which moves that up and down. The 4 moved it up 4 units. And that is the notes for graphing logarithms. I hope that was all clear. Again, if you guys have any questions, we can bring them to class and go through them together. But I hope you guys have a great rest of your day, and I will see you next time. Bye, guys.